Hello, ladies and gentlemen. This is Werkene again. In today's video record, I'm going to talk about the measure of dispersions. I hope you know what the measure of dispersion is. So, let me ask you some basic questions before I start explanation about this measure of dispersion. So, what is the measure of dispersion? What are the indicators that we use to measure these things or the measure of dispersions? Or what is which which indicator is the best indicator in terms of measuring dispersions of our data sets. So these are the basic brainstorming questions that I would like you to think before you watch this video, or try to answer it, try to address these basic questions that help you to understand about the thing that I'm going to talk. Then at the end, watch this video and see or evaluate yourself whether you addressed the concept of the measure of dispersion and the indicator that we use for for this purpose, for measuring the dispersion, as well as identifying the best measure of dispersion. So let me start my my explanation by sharing my videos or my slides. So here is a measure of dispersions. I think, when we say a measure of dispersions, like we are measuring, the dispersion of our data sets or the variation of our data sets. Simply, these things measure the variability of our data sets or the dispersions of our data sets. When we say the measure of central tendency, it helps us to in describing a set of data by a single number or by a typical value. The measure of central tendency actually summarizes about that data by single numbers. Maybe that single number is the mean of that data set or some typical value that can represent that data set. That is what the measure of central tendency do. The same is true for the measure of relative locations. It is about measuring the specific position or location of a given data set relative to the others. That is what the measure of relative location do. Now we are talking about the measure of dispersion. Dispersion means distribution. Dispersion means variation. Dispersion means how to the extent of the spread of your data point or your data sets. However, those things they do not provide us any information about the extent to which value different from one another or from the average values. Under the measure of central tendency or under the measure of relative location, we don't know to what extent a given data points are differ from each other or far from each other, or we don't know the extent to which they are differ from the mean. We don't know the distance between the given data point and the mean. Right? So that means we don't know the spread, we don't know the variation of our data points. So in this video record, I'm going to talk about the measure of dispersion. It is the indicator that help us to see or to measure to what extent our data point differ from each other, to what level our data point is different from the mean. What is the variation, what is the spread of the data points in that data set, to what extent they are far from each other, to what extent they are close to each other, to what level they are very far from the distance, from the mean. Right? So we are going to see the indicators or the variables that we use to measure this dispersion, this variation, this spread, right? So one of the indicators that we use for the measure of dispersion is the range. Range means it is the difference between the maximum and the minimum. In our data sets, we can get the maximum and the minimum, right? That is obvious things. The difference between the maximum and the minimum is the first initial indicator that help us to see the variation of our data points. If the range is very high, that means there is high variation in that data set. If the range is very low, that means the variation, the spread of the data set is not that much big, right? So that the range shows us, help us to know the distribution or the variation of the data point. For example, in your course, if some of you got like 199% or 99 point and some of you got like 20, Then the range in this case is 99 minus 20, which is 17. 17 is a very big number, therefore the range is really big, and therefore there is high differences, on the student's score for that specific courses, right? That's not a good thing. If the variation is very high, that is not a good, indicator, right? That's not a good indicator. It's better to have like more or less, the data points that are closer to each other, so that we can even predict the nature of the total population by using the sample data, if our sample data look like that. Another thing is, one of the characteristics of range is that, especially we can call this thing as a limitation, if there is an outlier in that data set, then the range is very sensitive to the outliers. For example, if the majority of your data actually from 1 to 10, but if there is one individual that score 99, right? So that the range is 99 minus, let's say the minimum is 1, then it is around 98, right? It's completely meaningless, or it is not a good indicator in the case when there is an outlier. Therefore, the range is also influenced by outlier. It is very simple one, but it is also very interesting. It's a common one. Of course, most of the time when you do some statistical regression or some statistical analysis, calculating the range is the simplest one, the common one. But if there is an outlier in your data sets, the range is not the better indicator. You need to use some other variables or some other indicator that can tolerate, or that can, not that much sensitive to the outliers, right? There are another indicator which are not that much sensitive to the outlier, so that you can use in that context that indicator, not the ranges. The other one is interquartile ranges. Interquartile ranges. It is helpful when extreme value or outlier exists. If there is an outlier in your data sets, the range is not a good indicator. Therefore, in that context, you better use interquartile ranges. What is interquartile range? Interquartile range is the difference between Q3 and Q1, the third quadrant and the first quadrant. Of course, you know what quadrant is. Quadrant is the measure of relative location. Actually, quadrant divided our data sets into four equal parts. The first one is called quartile number one. The second one is called quartile number two. The third one is called quartile number three, right? Quartile number one actually separates the first 25% of the data sets from the lowest 25% of the data sets from the rest, the first quartile. That means if the first quartile for a given data set is, let's say, X, that means 25% of your data value actually less than that specific values, X in this context. Simply, the first quartile separates, the first 25% of the lowest 25% of the data sets from the rest in a context from the higher one, 75%. It separates the first 25% from the other 75%. That is quartile number one. What about quartile number three? Quartile number three actually separates the highest 25%, the highest. That one is the lowest. Quartile number one is the lowest 25% from the rest. And quartile number three separates the highest 25% from the rest. Therefore, quartile number three is like below 75, and the quartile number one is below 25, and therefore interquartile range actually measure the dispersion or the variation of the middle 50%. It is the middle 50%. Quartile number one actually separates the first or the lowest 25%. Quartile number three separates, the highest 25%. What's left then? The middle 50%. Therefore, interquartile range measure the variation, measure the dispersion of the middle 50%. The middle 50%. One of the interesting characteristics of interquartile range is that if there is an outlier, because when we say outlier, it is a value which is very far from the data points. It is maybe the lowest or it may be the highest data values, but it is very, very far from the other data sets. That is outlier. It is very far from the mean. It is very far from the other data points simply. Therefore, those outlier actually excluded when we talk about interquartile ranges. Interquartile range is not sensitive to the outlier. There is no influence of outlier. Range is very sensitive, but interquartile range is not sensitive. But one of the limitations of interquartile range is that it actually the first 25% and the highest 25%, the highest 25% and the lowest 25% is excluded or are excluded from the data feeds. Therefore, we are talking about what? The middle 50%. Therefore, interquartile range is not inclusive. That is the problem. Because the highest 25% and the lowest 25% are excluded. They are not in the discussion. They are out of the discussion. We don't mind about their dispersion. We don't care about their variation. You see, that is the problem of interquartile ranges. Except that is so fine. Interquartile range is very powerful. Alright, now let's talk about mean or average deviation. This is also the third measure of dispersion. It is actually the sum of, it is a summation of an absolute value of the difference between a given data point minus the mean divided by n, the number of observations. This is what the absolute deviation is. This measure of dispersion is less sensitive to the outlier one. It is very good indicator for the deviation. It actually quantifies the deviation of the data points from the mean or around the mean. To what extent, to what level that our data points actually deviate from their mean. The distribution of the data points around the mean. That is what the mean deviation or average deviation measure. It's very powerful, it's very interesting. It's not also sensitive to the outlier. Mean deviation is not sensitive to the outlier. That's interesting. If there's an outlier, we can use mean deviation. It is not as sensitive as the ranges. But it has limitations. One of the limitations is that we don't know the direction of those variables, right? Because we are talking about in absolute values. Since it is in absolute values, we don't know whether that specific data point is above the mean or below the mean. Right? That is very essential things. Whether the spread of the data is below the mean, whether it is above the mean. When we say the mean, it is the average, it is something which is in the middle, right? It's like that. Mean is not, of course, not median, but it is something in average. Means it is, so that we need to know whether a given data point is above the mean or below the mean. One of the limitations of mean deviation is this thing. We don't know the directions. We don't know the direction. That is the problems. Of course, identifying an outliers. Outlier are observations that are far from the center of the distribution. When we say an outlier, it is an observation which is very far from the center of the distribution, from the center of the distribution, or from the rest data points. That is an outlier, which is very far from the rest, which is very far from the center of the distribution. These are defined as an observation, which are either, of course, by using quartile and interquartile values, we can get whether our data set has an outlier or not. If there is an observation which is greater than Q3, the third quartile plus 1.5 of Q means interquartile ranges. If there is any data set, if there is any data point in our data sets, which is greater than this value, then that point is an outlier. Or if there is any data point in our data sets which is less than these values, Q1, quartile number 1 minus 1.5 of interquartile ranges. If there is any value which is less than this point or above this point, that is an outlier. So this is the way we can get an outlier. Of course, in SPSS, getting outlier is as simple as clicking something. It's about clicking some kind of menus. Very simple, we don't need to worry that much, but the knowledge is very important. We need to know it. The fourth indicator for measure of dispersion is variance and the standard deviations. Variance is also one of the measure of the variation or the dispersion or the spread of the data points around the mean. The way we calculate the sample variance is like this: summation of xi specific data point minus sample mean, the whole square over n minus 1. Now the point is that there is a square here. Therefore, sample variance is very, very sensitive to the mean, to the outlier. It is very sensitive. Even it is very sensitive. Not slightly sensitive, right? It is very sensitive. Because we make it a square. Of course, we make it a square in order to make, in order to give more weight for the data point which is very far from the mean, for just to consider this variation or these outliers. However, sample variance is not a good indicator if there is an outlier. If there is an outlier, sample variance is very sensitive to the outlier. In addition to that, sample variance is square. And if the unit of measurement of the data point is like meter, for example, we are talking about, when we talk about sample variance, we are going to talk about square of that unit of measurement. If it is meter, meter square. If it is kilogram, it is kilogram square. It's like that. That is also another problem, because it's very difficult to make interpretation in that context, because it is in a square of the unit of measurement of the data point that may not make sometimes a sense or meaning. That's also another limitation of sample variances. It's very sensitive to the outlier. It's also difficult to make interpretations, because sometimes we get unit of measurement, square of unit of measurement of the data point. That's another limitation, another problem. The other one is sample standard deviations. This is square root of sample variance, a positive square root of sample variance. Of course, both sample variance and sample standard deviations always are positive. They are negative, because this one is a square, this one is a square root of these things. Always, given that we are talking about, when we talk about the numbers or number system, we have these things like we have natural number, whole number, integer, rational number, irrational number, real number, then complex number, and things like that. It go like that. So that's when we talk about complex number, we kind of there is a way that, of course, that is not in practice unless you are mathematicians. You don't need to think about or worry about like complex number. A real number is the maximum number system that we need to know as economists, or for rational decision maker. Real number is enough. Therefore, in the context of real number, always the square root of a number is always positive. But when we talk about complex number, the square root of a given number is positive plus negative. Positive or negative of, if the square root of 25 is positive or negative of minus 5, right? There is that thing. That's what we call as complex number. We don't need to worry about that. Anyhow, the positive square root of the sample variance. Therefore, the standard deviation is also what? Positive. Both of them are positive. That is one thing. But they are very sensitive to the outlier. Of course, standard deviation, in terms of interpretation, standard deviation does not that much sensitive. I mean, we don't have any problem with the unit of measurement, because Now the unit of measurement is not in square, rather it is the same as the unit of measurement of the data point, and therefore it's not that much difficult from the perspective of the unit of measurement when we make interpretation for standard deviation. That's not a big deal because now it is square root of some unit of measurement which is already made square, therefore that's not a big deal, right? That's not a big deal. That simply the unit of measurement of standard deviation is the same as the unit of measurement of the data point. Therefore, that's not a problem. But standard deviations, like it's very sensitive to outliers. That is the problem. And the other very important thing when we talk about standard deviation is that we need to believe in normal distribution. We need to assume that the data is normally distributed. Many times, most of our data, they are not normally distributed. That's also another problem. If the data is not normally distributed, using standard deviation is completely wrong. Unless otherwise your data is distributed normally, you can't use standard deviation. But in the standard deviation, if your data is normally distributed, you can use standard deviations. Another point is the coefficient of variation. This is also a very interesting measure of the variation of the data pointers from their mean. And even one of the interesting part of the coefficient of variation is that there is no unit of measurement. As you see, the coefficient of variation is the ratio of standard deviation to the mean, and therefore there is no unit of measurement here. We don't have any unit of measurement. These things cancel each other because the unit of measurement of the mean and the unit of measurement of standard deviation are the same, and these things cancel each other. Now it is standardized. There is no unit of measurement. That's one good thing. And the other very interesting part of the coefficient of variation is that it helps us to compare two data sets, two datas, right? Two data, maybe data from public policy student, data from social policy student. They are different groups. Then you can compare. Now it is standardized. There is no unit of measurements, and then you can make a comparison. Which data point, which data set has high variation? In order to answer this question, or in order to know which data set has high variation, we can use a coefficient of variation. Coefficient of variation. It is very interesting. There is no unit of measurement for the coefficient of variation. It helps us to measure variation of different data sets. Even to make comparison, we can make comparison of two data sets using the coefficient of variation. There is no unit of measurement in the coefficient of variation. That's also another interesting thing is when we talk about the coefficient of variation. The other one is standard score. This is also another very interesting, very powerful measure of variations. These things help us to know how many standard, now the unit of measurement is standard deviation. How many standard deviation the given data point is from the mean. How many standard deviation the given data point is from the mean. Yeah, it's very interesting. If the formula for standard deviation is this one, data point minus the mean over standard deviation. This is standard score, or sometimes we call it z score. And if this value is 0, that means mean and the data point are all the same. That data point is exactly all the same of the mean, because this thing is 0 if and only if these two values are the same or equal, right? Therefore, if the standard deviation, if standard score, z score is 0, that means that specific data point and the mean are equal. That is all that data point is. That data point is exactly all the mean. If z score or standard score is positive, that means that data point is above the mean. You see, if standard score is negative, that means that data point is below the mean. It's very powerful, it's very interesting to compare two data points. It helps us to know or to measure how many standard deviation our specific data point is from the mean, how many standard deviation. It's also very important in terms of checking whether there is an outlier or not in your data point. How you do so? Here is the way you do it. The score is used to detect outliers. A Z score less than -3 or greater than +3 indicate a presence of an outlier. This is very interesting indicator. If Z score is greater than 3 or less than -3, then there is an outlier. Look to your Z score values, and if you get a Z score value greater than 3 or less than -3, like -4, -5, -6, less than -3, then they are out. There is an outlier in that data set. Therefore, you need to go for that data set and you need to get that outlier and take appropriate measure before you use your data sets for further analysis. What you can do, you need to exclude that data set from that specific outlier from your data points if you want from your data sets. Or you may check whether there is some recording problem, whatever, maybe typing problem. You need to check it and you need to take appropriate measure if there is an outlier in your data points. Box plot provide another ways to identify an outlier. Of course, drawing a box plot is very simple in SPSS. We will see in practice how we can draw a box plot. So this is a box plot. This is the lower limit of your box plot. This is the upper limit of your box plots. This is the first quartile. This is the third quartile. And the difference between the third quartile and the first quartile is interquartile ranges. And the line between the first quartile and the third quartile is a median. And if you have any data points outside this limit, lower limit and upper limit, then that data point is an outlier. For example, here you see here, this is an outlier. Of course, spaces represent data outlier in two ways. One is in star, the other is in points, in dots. If actually SPSS inform you outlier in dots, that outlier is not that much far from the center of the data point. That is not that much far. It is outside the boundary. It is outside this boundary, but it is not that much far. It's not that much, very far from the center. But if there is a star outside this boundary, that outlier is really significant outlier. It's very critical outlier. Therefore, you need to work on it. You cannot use your data if your outlier is like very critical, very significant, or very, very far from the center. Therefore, you need to correct it. That is how you can make a decision of before you use your data sets, your data points for your further analysis. Wow, we did it. This is the measure of dispersion. It helps us to measure the variation of your data from each other as well as from the mean. There are a lot of indicators that we can use starting from the range to here the standard scores. The score or standard score is very powerful and very interesting unit, these standard scores. There is no unit of measurement for standard scores and it's very interesting. I hope this video can help you to understand what the measure of dispersion is, what are the indicators that we can use to measure dispersion or variation or the spread of the data sets in your the data sets in your research or whatever it is. And I hope this video record help you a lot. Thank you very much for watching this video record. In the coming video or in the next video, we'll talk about the measure of distribution shapes, relative location, detecting an outlier. Especially we may focus on more on the measure of distribution shapes, how we measure shape of our our data sets. I will talk about that thing. Thank you very much. See you soon. Have a nice time.